compounds and chemical formulas. We've talked about little aspects and we've kind of skirted around the topic, so let's push it a little bit harder. Does that look familiar? Yeah, what is it? It's chemical. That's a good first step, yes. That is the chemical that if you bothered to get up during the middle of the class to get some refreshments at the back, you were probably ingesting. That is caffeine. Right? So there's all sorts of different pieces behind that. If we asked you to do that for every single compound, you would probably get irritated. Okay? Because that's a lot of work to have to draw out the structure. So what do we do instead? We could go through and write a name. Writing the name caffeine, though, does that give us the same information as all of that? I don't think I spelled that right, but it's close enough. Okay, does that give us the same information that we had in the structure? What information did we lose by writing caffeine? We lost details. Get specific. Okay, the structure. I lost the structure. I lost the composition. Right? I don't know what elements went into caffeine. Okay, so what else could we provide instead of going through and writing out the name? Yes, we're going to have to lose some aspect, but do we really want to lose structure and composition? No. So what could we come up with? We could use a chemical formula. In that chemical formula, what might I specify? Okay, I have carbon in there. I have hydrogen. I have nitrogen, and I have oxygen. So I could write it as CHNO. Okay. I might want to classify and put a little bit more information in. How many of each of those elements are specified within it? So I could go through my picture of my structure. I could count them out. How many carbons do I have? 8. Okay, I'm just going to trust you. Okay, so I've got 8 carbons. How many hydrogens? We'll just accept 10. It's fine. Nitrogen? 4. Oxygen? 3. 2. Okay. 2. I wasn't counting. I'm trusting you guys to count. Okay. That formula looks kind of confusing. It's a little bit clarified because the numbers are colored, so that could help. I could also go through and have color-coded it this way, right? Whoops, that didn't work so well. Let's try that again. Right? Doesn't that work to color-code that? Okay, sure. How many of you have that many colors? Okay, laughter, I'm going to guess that's a no. Okay, so we want to come up with a system that would allow us to specify that information and not get confused. Okay, so we could just go through and say, well, the number in front always counts. What if I have 3 of these molecules? Where would I write that 3 now? Okay, we did a 3 here. That could get confusing with 38. We could also drop parentheses around it. So we're now having to specify more information and layers on top of this. Wouldn't it be nice if we could drop or change where we represent that information to help us not have to add context of parentheses? Okay? Instead of specifying the number of each of those elements out in front, we could leave the front to represent the entire thing. So the only number that gets written in front is how many of that entire thing is present. But then that means this 8, 10, 4, and 2 have to be moved somewhere else. Okay? As we've seen with other formulas, like H2O, where did our number get written? In the bottom right. And our formula can become C8H10N4O2. We've now coded that information behind it. We know how to put that together. Okay? Some of that we kind of assumed and we talked about it within H2O. Okay? It becomes a bigger and bigger issue when we start to now work with these formulas. And we have to constantly remind ourselves that that information is there and that's what it's referencing. The subscript number after a symbol, or is referring to the symbol immediately in front of it, okay? And it's the amount of them. Kind of make sense? Okay, so representations we could go with, H2O, C6H6O6. Can I get rid of that thing? Yes, I can. Okay. We're now coding and saying that 6 represents the number of carbons in the compound, that 6 represents the number of hydrogens, that 6 represents the number of oxygens. Okay? That's what that information encodes. Okay? If we look at it, carbon, hydrogen, oxygen for that formula, nice left to right. What happened when we moved to the next one? Is the order the same? No. Not only is the order not the same, what else did I do? I split the hydrogen out. I put that hydrogen out front as opposed to keeping it embedded in between. Why?
It has a different structure, or it's bonded to different elements.
What would be a formula for that? How many carbons? C2. How many hydrogens? 4. How many oxygens? 2. This formula here versus that formula there. I wrote them different. Why would I write them differently? What is the point to changing the sequence of those symbols?
To represent the structure, where the bonds are.
Close. What do you got?
Pretty much the same thing as David.
Okay. We're trying to represent structure. So this hydrogen is connected to that carbon, but those 3 hydrogens aren't connected to the carbon? No, that's definitely not what that shows. That hydrogen out front is connected to what? Oxygen. How'd you pull it out as the oxygen that it was connected to and not, say, the carbons? There's 3 hydrogens that are all connected to a carbon. There's only 1 hydrogen that's connected out differently. So you're saying, based off of what your approximation is, you could see that split. Why would we call that hydrogen out as distinctly different than the rest of them? Different bond. Why is that important? HCl versus H2O. If I throw those at you, are you going to react differently to one of those? Yeah, why? One's an acid. That chemistry is dangerous. We want to call attention to that chemistry. Why do we write it as HC2H3O2 as opposed to C2H4O2? Because the chemistry is a little bit different. Those are both going to represent the exact same structure and compound. But when I write it as C2H4O2, what have I done to the function or the chemistry of that molecule? I've hidden it. I've made it less obvious. By pulling that hydrogen out front, what have I now done? I'm drawing attention to it. So I'm changing how I format and present the information to draw attention to particular chemistries.
Why?
Why would I do that? Okay. There might be a rhetorical purpose behind that. What would that rhetorical purpose be? You responded differently between HCl versus H2O, right? Because HCl was an acid. H2O, we don't qualify as an acid. Guess the reactivity of this particular compound. It's an acid. By pulling that hydrogen out front, I can now flag that as an acid just by changing the sequencing of those elements. Okay? So there's a rhetorical choice to show that information. There's also a rhetorical choice to say I don't want to show the structure. What's the choice to not show the structure? I'm lazy. Okay? And I've decided that the structure wasn't all that important. All I need to do is draw attention to the chemistry of that as much as possible. Okay? So when we think about our chemical formulas, they don't all follow the exact same pattern. We will change the location of individual pieces depending on what we are trying to highlight as the functionality of that compound. Sometimes that functionality is within the scope and context of what you guys have seen. Sometimes it's not. Okay? At this point, what you need to be able to recognize is that it's calling attention to a difference. You may not know what that difference is necessarily yet, because we've really only addressed one difference when we talk about formulas, acids. Okay? That's the only one that differentiates.
So to clarify, it's not actually a different chemical.
It's not actually a different chemical. Okay? All we're doing is changing the location of the atoms in our formula so that we can better represent it. Okay? It's reactivity.
Basically, each of those are synonyms, and depending on the context, you would choose a different word to fit the context and rhetorical intention.
Let's see. Can
What,
I do
language
it?
and chemistry?
Yep, I can do it with this one. So, dang it, can I undo? Yay! Look at that. There it is. What did we say our formula was for that? What's the formula for the blue one? Jerks. Would I expect those two compounds to have the same reactivity? Okay. I've changed the location of those atoms. Okay. Are you going to have the same response to me if I walked in one day and my arm was growing out of my forehead? Okay. By changing the chemical location of where those things are, it drastically changes how it chemically interacts. The structure provides that information. Does the formula? No. Okay? But if I do a very subtle change between those two formulas and say for that red one, I'm going to draw attention to the fact that it's an acid and write it as HC2H3O2, I've now provided just a little bit of context there to say that the blue one's not valid. Okay? So the formula can be written in a way to give you more information. Okay? It can also be written in a way to completely remove information. Okay? So I want you to be aware of that because I'm an organic chemist and organic chemists care about structure. Okay? Structure does lead to function. At the same time, you don't need to know structure to learn function. Okay? Most of what you do in general chemistry removes the structure. Why? Because you got to draw big, nasty structures. Okay? If we had to do that at the same time we're trying to learn the language, it becomes challenging. Okay? So we step away from structures and we go into those formulas. Okay? C2H5OH. I split out the hydrogen again. Notice, where did I put the hydrogen this time? Put it at the end. I didn't put it in front. Why did I not put it in front? Not an acid. Okay? We could go through and say, oh, that's OH because that's hydroxide. We'll push that a little bit harder later in the semester. No, hydroxide only exists when it's ionic. To be ionic, what do we need to have? A metal and a nonmetal. Where's our metal? There isn't one. So that's not hydroxide. Okay? It is structurally very similar to it. Why am I pulling the hydrogen out there? Where's the hydrogen connected? To the oxygen. I've provided a little bit of context that if I was now to attempt to draw the structure, I would be more likely to draw the correct structure than not. Okay? We see another one here. What was that formula? That's C2H4O2. Wasn't that the same as this? Yeah. Why is it again written slightly differently? Okay. we're actually trying to convey more structural information. CH3. God, go away. Not you. You guys are fine. What do we have there? CH3, which is then connected to a carbon that is connected to two oxygens that is then connected to a hydrogen. So by changing how I organize those letters, I can get different structural information. Okay? Do I lose the hydrogen in front? Is the hydrogen in front? No. So, yeah, I did lose that. Okay? But if I know how to interpret this, I can still come to the same acid conclusion. But that requires more knowledge because I have to be able to look at this and immediately jump to that structure. Okay? How do you look at a formula and jump to a structure? Practice. You're not there, don't stress. You should be there because it's cool, but that's okay. Okay? Last one. What's different about the last one? It's got a plus sign in it. Are we looking at just a chemical formula? No, what are we looking at? I'm looking at a chemical equation. What's the organization behind how I take different chemicals and I react them with each other? I show a plus sign in between. Those things, when they react, how do I know that I'm reacting them? A plus sign could be useful, but that could just mean I have both of these things, right? A plus could be an and. How do I know I'm actually doing a reaction? I have a reaction arrow to signify that information or that new thing is happening. Okay? All of this stuff is embedded behind the language. Some of it gets pointed out, some of it doesn't. If at any point you're like, I don't really know, ask. Make sense? Okay. So, entirely different subject. So let's just shift gears. Measurements. Okay? Some of this is review. Some of it is different. So if you think it's review, that's fine. We'll speed through it. I've got some of the slides with red titles because they aren't review. Or they are review. Okay? So we want to be able to quantify our experiments. To quantify, we need a number and we need a unit. If I just say 2, what does that mean? It means 2. Okay. $2, 2 sheep, 2 lights, 2 fingers. As soon as I specify the substance that number is tied to, I can change the meaning of that number. Okay? So numbers in and of themselves don't hold meaning. They only hold a value. Science is not about values, which sounds kind of weird. Okay? It's about putting meaning behind those values. That meaning comes from our unit. That unit has 2 pieces, a measurement and a substance. Okay? When we said 2 sheep, what was the measurement? The number was the 2. What was the measurement? What did I measure when I said 2 sheep? The number of sheep. It was the pieces of whole sheep that I saw. Okay, the substance was sheep. Okay, so the measurement becomes kind of hidden behind us when we're doing a raw counting of particles. Okay? But what if I said 2 pounds of sheep? Now I have a measurement clearly tied in there with the pounds. I could say 2 liters of sheep. And you're like, what? That's stupid. You all started laughing. Why are you laughing at me about 2 liters of sheep? Why is that an odd unit? Yes. When do you use liters? Liquids. Are sheep liquids? Usually not. And so what you were envisioning is, what is Mike doing at home blending up his sheep? Right? We have different measurement systems for the different phases of materials that we work with. Okay? And we tend to associate them with those individual phases. That doesn't mean they can't be cross-pollinated. I can blend sheep. Okay? I have the ability to do that. Okay? I may not want to. Okay? That may be a really bad idea, but I have that ability. Okay? I could also do 2 inches of sheep. How did I get it? Well, the steak that I made was 2 inches tall. Yeah. Okay? So we can change how we go through and reference those, and it significantly changes the meaning. Okay? And the reason I want to hammer this home is we're about to move into the concept of conversions. And in conversions, you are very used to dealing with conversions. If I say 36 inches, you can tell me how many feet. That was really, really, really fast. That's fantastic because you're trained to deal with those units. But if I say 36 moles, how many atoms?
What?
Yeah. You're like, what do atoms have to do with fuzzy little animals? Okay? If you don't have that context, you can't do that conversion, and that's where it becomes challenging. So this unit, when we talk about conversions, what you need to do is not be like, I can totally divide 36 by 3 or 12 to get 3, okay? But what was the process that you used? How did you know to divide by 12 inches? Okay? That work is something that you need to be focusing on within this unit when we talk about conversions. And it's all tied back to these units. The instant you decide the units aren't valuable is the instant you get the question wrong. Okay? So, what are our different measurements? We've got length, mass, volume, time. Those are all kind of fun things. We get a bunch of different ways that we could measure these. Okay? I could say this table was 8 pens long. Who the heck measures a table by 8 pens? That's a stupid measurement system. No, that's not. That is a perfectly socio-cultural, acceptable mechanism in my household. Okay? And now you're laughing like, well, that's a stupid household. Okay? It's all dependent on that norm. If we're going to work within science, we need an acceptable measurement system that everybody can agree upon. Because if we can't agree to those systems, the entire ability to communicate those different measurements fails. Okay? That's a really big issue. Okay? For most science, we shift to the metric system. Okay? So within our metric system, length, mass, volume, time. Our length we typically measure in meters, mass, grams, volume, liters, time, seconds. Okay? And they call this the basic unit. And I'm going to change that around a little bit. We're going to reference that as the core unit. Okay? Because what do you think of when you think basic unit? Smallest unit possible? It's a bit of a stretch. We might go with common, right? The basic unit is the one that we would most commonly use. Okay? When you go into lab, how many times are you measuring meters? Why not? That's really big. How many times are you measuring grams? Well, that's not too bad. Okay, we use that frequently. How many times are you using volume as liters? Never. Why not? That's a massive volume of chemicals, which increases a safety risk for you and a very large hazard chemical waste disposal cost to us. Okay? So we will change those volumes and mutate them to match systems that we want to use commonly. Okay? So what these are the core system which we will mutate. Okay? They say basic isn't officially true because the basic unit for grams, or for mass, believe it or not, is not grams, it's kilograms. Grams was derived after kilograms, which seems really weird, but that's how it was created. Why might that be? Why would we have massed things as kilograms, not as grams?
Well, they have an actual physical kilogram reference in English.
So we'll get to that too in a second. Why would we have done kilograms instead of grams?
More sensitive scale based on things.
Think about the origin of the measurements. Okay? If I'm going to measure distances, do I really care how small my pencil is? No, I'm going to care how long it's going to take me to get to the next city. Okay? How tall is that building? Right? When I think about mass, do I really care how much a little leaf weighs? No, I can lift that. But I can't lift this dude next to me because he weighs 2 stone. What the hell is a stone? Right? It's a unit of mass that they defined when they first started. Why would they have picked stones? Because they freaking had stones. That's how they created the base system. Right? But what happens when we go from, say, England to France and they have different stones? How do you make that comparison? So we would need to establish a defined system. That's where, yes, there are defined kilograms, grams, liters, meters, and seconds. They are very heavily protected because if anybody goes in and messes with them, what happens?
Everybody gets messed up.
Everything gets messed up. Right? So these systems are built off of materials that don't change their properties. For instance, if I say, we'll come back to that. I lied. I'm not going to talk about that yet because we haven't addressed that. Okay? Well, we could do the meter. Okay, length. How about if I used a piece of wood to just be my defined measurement for a meter? Anybody worked with wood? Okay. What happens when you first cut it? Is that when you should measure the meter?
Nope.
Why not?
It shrinks.
It shrinks. Why does it shrink?
Water counts it.
Water leaves it, which means water could also go into it. What happens to the length of my meter? Changes with what? The presence of water. You're like, well, I just won't put it in water. What did we just exhale? Water. So just by having someone go in to measure the length of the meter, you've now changed the water pressure. You're changing the length of your measurement. That's problematic. So what could we use instead of wood to make that measurement? We could use some kind of metal that is less sensitive to those changes. Does metal still change its size?
Yes.
Yep. Okay, that's how thermostats work. Okay? So we have to be very selective about the materials we use, and we have to be very controlled about where we store them. Okay? Which is kind of relevant for project number 2, right? Where do you have those chemicals stored? So, let's take a look at some measurements with uncertainty. We got a red slide here. So you guys should all be good at this, but I'm throwing a new example at you. There's my little blue arrow. Where is it? I see what you're doing. Yeah. What becomes problematic with this? Do all those numbers have the same sig figs?
Nope.
No. Okay. That very first one is saying I am guessing at the 10th place. Okay. If that's the case, that 7 doesn't hold a lot of meaning. The next one says I'm guessing at the 100th place. What does that mean about the 7? That it is absolutely true. 2 different measurements, 2 different interpretations off of the exact same device. That's a problem. Okay? That's only a problem because you haven't been trained how to make those measurements. You have to report all of your obvious digits and then one guess. Okay? So the 0.7 doesn't work. How about the 0.756? We're now guessing at the 6th, that's okay, but now what you're saying is that 5 is an absolute truth. Do you know anything about the 100th place?
Nope.
Nothing. Which means this number is now assigning more value than the device tells you. That's a problem. Okay? So you have to be able to use the device as it was intended. Make sense? Okay. So let's change it around a little bit because I forgot I didn't actually want it to be 1. Now what's the measurement?
0.075.
Okay. 0.075. Okay. That extra 0 that we had to insert in there is kind of important because that told us where to place that 7. Okay? Be it in the tenths or the hundredths place. Make sense? Okay. How many sig figs? 2. 7 and the 5. The zeros are placeholders. Okay? That's a challenge. We'll come back to that. Okay? New measurement. It's not that much more difficult. It's not like I moved that thing somewhere. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So those are marks that hundreds. So where's our measurement? Okay. 750. Okay? And then because we got a clarification on the oh Jesus, how many sig figs? It's only 2. This goes back to the meaning. Where did you guess? Which of those numbers is an absolute truth? The 7 is an absolute truth. Is the 5 an absolute truth? No, the 5 is a guess. What is the point of that 0? That's to tell you that the 5 belongs in the tens place. That 0 does not hold meaning. Okay? That is exceptionally challenging. But that's what we're doing when we're looking at sig figs. It's all dependent on the device that we're using. And what we're trying to do is to make sure that when we report information, we know how to report it so that we don't add meaning to it by saying there's 3 sig figs. Because if we say 3 sig figs, you're saying you know that that 0 is not a digit between 1 and 9. Nothing about where that arrow is pointing gives you any information about that. Okay? We also don't want to remove meaning by then saying that 5 didn't exist. I don't know where it is between the 7 and the 800, so I'm just going to call it 700. Okay? At that point, I've now lost meaning with that 0. Because I know for sure it's larger than 700. Make sense? Okay? So that's where sig figs become challenging, and it's ultimately coming from our measurements. So if we look at our Sig Fig rules, there's 3. Okay? Your textbook gives you 5 or 6. I've seen multiple people attempt to come up with different Sig Fig rules. They all fail at one state or another. Okay? These will always work. Okay? No one has disproven them. You do have to be able to manipulate them. Okay? So let's go back with our initial measurement that we had. 750, right? How many sig figs did we say that measurement had? 2. Let's follow the Sig Fig rules. 1 through 9 are always significant, which means 7 and 5 are significant. Okay? The next 2 rules are all about the 0. Is it significant or not? I have to decide by the placement of a decimal point. Okay? If I include a decimal point, I'm now adding meaning to it. If I let the decimal point just ride as implied in a particular location, I'm not adding that meaning. So if we go through no decimal point, rule 2, the 0 must be controlled by significant digits to the left and right. So let's take a look at that 0. Is there a significant digit to the left of it? Yes, fantastic. Is there a significant digit to the right? No, which means the 0 is not significant, and what do we end up concluding? That we got 2 sig figs, which is exactly what our measurement device gave us. Okay? That's the point of these rules. Okay? We got a bunch of examples there. Was that 8? Okay? Do you want a hot second to try and go through and do those? In theory, you've already done them, right? Yeah? Were there any that you would like me to look at in particular? Or you're all like, no, we're fairly good. What do you got, Dean? Okay, well, should we test you?
I was looking at the very bottom right one.
Bottom right, here.
So 2 significant digits?
3.
Just 0.
The 1 and 2 are significant digits. Okay? We have a decimal point. So what's our rule? If there is a decimal point, then the 0 needs to be immediately preceded by, so a significant digit to the left of it. Let's start with our very first 0 on the left. What's to the left of that 0? Nothing. That's not a significant digit. Okay? What's to the left of the next 0?
A number.
Is it a significant digit? To be significant, we would have had to establish that it was significant, or it was 1 through 9. Are either of those conditions true? No, which means not significant. Last 0, immediately to the left of it, what do I have? A significant digit, which means that 0 is significant. I get 3 sig figs. I get kind of excited about it because it's 3 rules. It's cool. Like all the other textbooks list out like 5 or 6, which is a whole nother history chapter in and of itself. Okay, if you're interested about that, we can talk about that. Right? But sig figs, those will work. Is there a question there? William? You're thinking about it? Pondering? Okay.
So the bottom left is also 3.
Bottom left, what do we think? 1, 2. I have a decimal point, which means to be significant, what do I need? Is that a significant digit?
Yes.
How about that next 0? What's to the left of it? Which means? 4 significant digits. Okay?
Why was the placeholder 750 just 2?
Why was the 750 just 2? What was specified? No decimal point. If I want that to become 3 significant digits, what do I need to do? 750 decimal point. Whoa, hello. But nobody does that. That's because most people aren't concerned about significant digits or the precision of their measurements. If you're a machinist, do you care?
Yes.
Hell yes. Okay, virtually everything you do is super, super precise. You have to be very careful behind that. And you might argue, well, but I've never had to worry about it if you've been a machinist. Okay, that's because in those cases, you end up using devices that all match the same precision. Because all of your devices run the same precision, you don't have to worry about differences in precision. But if, say, we measure density using a balance that measures out 4 sig figs and, volume that measures out 2 sig figs, do they have the same precision? No. So we end up getting a disconnect between how those things align, and we have to figure out our sig figs more appropriately. How important are sig figs? What's the speed of light? I'm just checking to see if anybody knows. What? Three times 10 to the 8th meters per second. 2.99 times 10 to the 8th meters per second. 3 versus 2.99. How big a deal is that? Right? You might be like, oh, that's not that big a deal. It's just the same thing. If we use 3 versus 2.99, we don't make it to the moon. Okay? We miss the moon or we crash into it. Okay? To travel to Mars, we need to know speed of light to 10 significant digits. Why? If we don't know it to 10 significant digits, what happens? We either crash into Mars, okay, or we go flying by and never make it back. Okay? So when we look at astronomical distances, big distances, we need those significant digits. We're not doing astronomy here. Why do we care? We're going the other direction. In chemistry, we're not going to astronomical, we're going to atomic, which means we're now flipping all the way down to the smaller end of that spectrum, which means we need it at that level. Okay? most of the measurements we actually take in the lab, we're using with kind of round 1 gram measurements that aren't that big of a deal. But if we want to scale out to know how many atoms are present, okay, which story for another day, okay, we do need a little bit more precision behind our measurements, okay, and our numbers. First, JC, I think. Did you have a question? No?
No.
Okay.
Because then you said when I talk about astronomy, so like back there, one.
I guess going back to the 650, so 120.0 versus 650 changes the amount of significant figures. But to me, the 750, the decimal and the following zero is implied. Why is it not implied? Just because it's written.
The following zero is not implied. You're right. It's not.
But in the case of 120.0, it's a significant figure.
In the case of 120.0 is the zero implied? No, it's explicitly stated.
Right.
Why do we need to explicitly state it?
Not to get what I'm asking.
To nail down that precision of the instrument.
Right.
Okay? That's why we have to explicitly state it. Okay? And yeah, there's a massive gray area between it, and we have to be very careful to follow the rules carefully, because if we deviate outside of it, it introduces all sorts of, well, how many did you actually mean? Okay? Where is the precision of your device?
I got you. But
Right.
going back to the machinist thing, if somebody came to me and wrote 10 inches, all right, I got you, but if they wrote 10 inches, 10.1,
That's now going to change what you have to do as a machinist.
right. Well, I
Exactly
know
right.
that they went to 10,
Yep.
and that's what you're saying here.
Yep.
Okay.
Measurement versus exact. This is fun. How many quarters are there? I thought it was 7. It's admittedly a little blurry. So there are 7 quarters. So of course, what's the question going to be?
How much money is it?
No. Sig figs. How many sig figs are in that? 1. So if you're saying only 1 sig fig, then you're saying an equally valid interpretation of that, 6.9. Are there 6.9 quarters there? No, so that's not equally valid. Okay, so we need 7.0. Cool. I understand. So an equally valid interpretation of that image would be 6 or 7.09 quarters. No, that's not valid, Mike. You're an idiot. Okay. How many significant digits are there?
7.00. Actually, no. You can do 7.00.
7.00.
So counts as 2. Because they're still significant. I mean,
How many zeros do I need to include in there for you to be like, or where I can't F you up and drop in a 9
at
afterwards?
least 5. You'd be like
You could absolutely tell me the number of zeros. Sort of.
infinite.
You need an infinite number of zeros, because then I can't drop a 9 after it, because you're saying an infinite number of zeros. I'm not allowed to add another 9 after it, which means how many significant digits are there?
Infinite.
An infinite amount. So exact things have infinite sig figs. Okay? If this was now a pile of quarters, would you be able to count it as easily? No, and you would probably start to approximate. Okay? So at some point when we start counting, we start introducing an error to it that it's no longer an infinite amount of sig figs. That becomes a challenging thing to deal with. Where's that line? Okay? It's one that's kind of right in front of your face. 10. When you start counting beyond 10, you're introducing error. And it's now questionable to say it has infinite sig figs. Why?
You can't decide.
Where's my 11th freaking finger? Careful.
Use the knuckle. Palm.
We could create a new system where we start changing out the counting system. Okay? And you can continue to do that. Eventually, you're going to reach a point where you're like, I can't count beyond that. My new system now has flaws. Okay? Greg talked about the knuckle system, right? Base 12 counting systems. It's still going to reach a limit where you run out of the ability to interpret. Okay? I would argue once you're beyond 10, you're introducing error.
Have you seen the thing where they count months with their knuckles and they go like, how many days are in a month?
And all I see there is a knuckle in my face. And it just makes no sense to me. But yes, I understand that. It's just like you're just punching me in the face. I don't get it. Okay? So, measurements where there are direct counting, when you're beyond 10, you should be considering sig figs. Okay? There's other cases that are also exact. "12 inches equals how many feet?" One, I know. Freaking conjugations. How many sig figs?
For which one?
It's a single expression. So, how many sig figs?
We're going to be wrong.
One.
It's a trick question.
It's infinite.
Oh, because they're whole numbers.
It's not that they're whole numbers.
They're exact.
This is a definition. We have defined this to be true. Okay? You can't go out into a native population that has never experienced the rest of the world and say, tell me how you measure 12 inches is equal to 1 foot. Is that true? And they're going to be like, what the hell are you talking about? Okay? That system, you talk to most of the world, they're like, what the hell are you talking about? It's just a stupid system.
Except for one bit.
That's not officially true on a couple accounts for that one, but let's deal with that one later. Because we actually converted to metric to make that leap, number one. And number two, there's several other nations that have now also made it. Okay? So, okay? If it's an exact measurement, like accounting, that's one thing. If there are definitions, if it has been defined to be this, then it's infinite sig figs as well. Okay? So, why do we care? What's the answer of this?
115.63362.
You're good at the long addition there, right? That's pretty impressive. What did you say 5 and 8 was? Yeah, I was fishing for that.
6.511.
All right, that's what your calculator spits back. Did that correctly take into consideration the precision of each of the instruments being used to make the mass? No. This first measurement here is only precise to the tenths place. It is not telling you about any of those other places, which means those other places could be zeros, in which case this measurement is correct. They could also be nines. Does that get you a difference in your answer? Okay. If they're zeros, it looks like the cat was already out of the bag. We did that math. The other one, in case the cat wasn't out of the bag. Okay. Those are two different measurements. Where did they vary? Where are they different? They're different in the decibels. Good. Where specifically did they vary? In the tenths place. Go back to the measurements. Where was our least precise place? It's the tenths place. Right there. I know no information after that. So our rule for addition and subtraction is our result is only as precise as the least precise measurement. Why? Because those sequence of numbers that come afterwards could be anywhere from 0 to 9. And if they're 9, that changes our measurement. Where does it change it? At the exact same position that our least precise place appeared. Okay? So this isn't just some random, we just made it up. That's just how it does it. Okay? You can look at actual calculations to see where these things come from. Okay? So that's addition, subtraction. Are there other mathematical operators? Multiplication, division. The result is only as precise as the measurement with the fewest significant digits. Is this the same rule? No, the rule has changed. Why does the rule need to change? The type of operator being run has changed. How does that affect us? So what is the area of this square? How do you calculate it? Length times width. So 7.28 times 4.6, right? Okay. We multiply that out, what do we get? 33.488 units squared. That's what our calculator spits out. Okay. That assumes that the 4.6 has 3 sig figs and that third one is 0. Does it have to be a 0? Nope. What could it have been? 9. What happens when we run the calculation with that as a 9? The number changes again. Where does it change? The ones place. Okay. And we might say, well, the ones place. So it's precise out to the one. But neither of these numbers are the ones place. The rule changed. What's our rule? The number of sig figs. Number of sig figs in 7.28. 3. Number of sig figs in 4.6. 2, which means our answer can only be reported to 2 sig figs. If I report only to that ones place, how many sig figs would I have? 2. The rules follow how the calculations run. Which of these is the correct measurement? What is our area for the square? 33 or 34? 33. Remember the 34 came because we said we didn't know what that one was. We could make it a 9. Okay? So the area for this square that we would have to report would now be 33 units squared. Okay? So we have to appropriately deal with those rules. I did hear someone say, sorry, round. Okay? Should rounding matter in this case? These are the digits that I'm allowed to report. What's the next digit? A 4. Should you ever round up from a 4? It's your paycheck, probably. Okay. If you're the one paying, probably not. Okay? That 4 is low enough that we aren't going to deal with a rounding. Okay? But could rounding become an issue? Yes. Okay? So we need a rule system to do that. This is the rule system that I use. Anybody a bit nervous about what I just said there? That I use. Son of a, really? It could change depending on the person? Yes. Okay? This is straightforward enough. I accept it and I use it. I also try to ensure that when we run calculations, that I'm very careful behind significant digits to ensure that we don't encounter problems. And this is one of my biggest issues with significant digits. We harp about how important they are in class, and then what do? We give you example problems where the significant digit rules weren't followed. Okay? Or we give you exam questions where the significant digit rules weren't followed, and it's usually settling on the rounding. Okay? We are not very good about being consistent with our significant figures. Okay? And what I will probably get from most faculty that then complain, well, yes, we are. We're perfectly awesome. We're just off like 10% of the time. So you're not correct all of the time, and now you're relying on students to trust that you're doing that correct. Okay? That is a challenging thing to do. Okay? It's up to you. You can definitely press faculty that aren't doing that appropriately. Okay? And you'd be like, you just said these were the rules to follow. You're not following your own rules. You want to step up on that? And yeah, this is where Greg provided you the tools to rhetorically achieve your goal, okay, which should in theory be getting points back, not creating a fight with an instructor. Okay? Fights with instructors typically don't end well with students. Okay? Just so you know. Okay, typically. Okay? So, these are the rules I use. If you notice me screwing them up, by all means, feel free to call me out on it. I'll try and watch it and make sure. Okay? It is something that I do try and track very carefully in the exams to make sure that that kind of rounding issue doesn't show up. Okay? But I can't guarantee it. Okay? It will be compounded by multiple other issues that we'll talk about later on. Okay? So, you want to do a little bit of practice? Think you guys can do it? Yeah? Okay. So we got 6 questions. Try and figure them out. If you got questions, raise your hand.